Then we go to our next speaker, Dr. Zhenglong. So Dr. Xu is from the Department of Industrial and Systems Engineering at Hong Kong PolyU. So Dr. Xu received his bachelor degree in material science and engineering from Zhejiang University and a PhD degree from the Hong Kong University of Science and Technology. Before joining the PolyU, he did the postdoc in the Seoul National University, and his research interests them focus on the design, fabricate, and characterization of advanced energy materials and devices. Without further ado, let's welcome Dr. Xu for the presentation.
Okay, thank you. Can you hear me?
Yes.
Okay, thank you very much for the chair's introduction, and I really appreciate Dr. Aubach's presentation, who is a pioneer in the battery field. And today I want to share our recent work about calcium battery, which is relatively new to you, but I think for Professor Aubach is nothing new, which have been studied about 20 years ago. Okay, so I'm Dr. Zhenglong Xu from ISE department at PolyU. And before that, at first we need to understand why we need to transfer from the lithium battery to other battery systems. But lithium battery is so successful that which have been developed around 30 years before, which use the transition metal oxide as cathode and graphite as the anode. And during charge and discharge, the lithium-ion transfer between anode and cathode, we call it a rocking chair mechanism. And over the past 10 years, you can say that this card refers to the electronics. This market almost saturated for the lithium-ion batteries, but a new market emerged. We call it electric vehicle or green transportation, especially in recent years that many countries around the world have launched the program for the carbon neutrality, and for the carbon neutrality and green transportation. So in the near future, large amounts of lithium battery will be demanded. Well, with a large amount of lithium battery demanded in the future, we need to consider the lithium resources. Lithium resources in the Earth's crust is relatively low. You can see that here is the elemental abundance in the Earth's crust. That the lithium abundance is only 22 ppm, which is much lower than the others. So that is why in recent years, with the booming development of lithium-ion battery, that the lithium carbonate, which is the raw raw material of lithium resources, there is a price spike, right? So in the future, we need to transfer to some other battery systems use more abundant element resources. System at current stage and some others. But today I want to share our work on calcium, which I've very rarely visited by the community. Well, the structure, or the configuration of the cell for lithium or for post-lithium battery like sodium, calcium, magnesium, they are very similar. We all use a positive electrode, negative electrode, and to drive the force and back shadow of the charge carriers. Okay, so here is a summary of the post-lithium-ion battery systems, including sodium, potassium, what Dr. has presented to us, but also some others like magnesium, zinc, or aluminum. You can say that compared to the monovalent system, divalent or trivalent system have a unique advantage is that the divalent or trivalent charge carrier intercalation or intercalation will involve doubled or tripled electron transfer per charge carrier transfer. So that means potentially higher energy density or higher capacity. Okay. And number two is that compared to lithium, which is very scarce in the Earth's crust, the magnesium and some others, which are very rich in the Earth's crust, which suggests a lower cost for the potential battery systems. Okay, and compared to other multivalent battery systems, cation is more promising because you can see that redox potential cation is minus 2.9, which is the lowest among the multivalent systems. So that which means we can obtain a high voltage cation battery system compared to others. Okay, but the development of cation battery is not straightforward. In fact, it's more difficult than others. So here I want to give you a brief description of the development history of other multivalent battery systems. I mean, I only involve the breakthrough report. For the Maxim battery, you can see Professor Auerbach reported in 20 years ago, right? More than 20 years ago. His breakthrough work is that to intercalate cation ion into MO6 S8 as cathode, which is very stable. And after that, many work follows this work to develop cation batteries. And for zinc ion battery, the breakthrough work comes out in 2012. Professor Fei Yukang at Tsinghua University reported that the zinc ion battery use a zinc nitrate aqueous electrolyte, use manganese oxide as a cathode, and to reversibly cycle this battery system. Well, nowadays people, many people work on zinc batteries. Well, for aluminum battery, in fact, it's been developed tens of years. Well, the breakthrough, in fact, was reported by Professor Hongjie Dai in 2015, published a paper on Nature that used graphite as cathode and ionic liquid electrolyte to achieve over 7,000 cycles for this battery system. Well, up to here, you can see that cation battery, I mean, the breakthrough does not appear. Well, here you can say, I want to give you a brief description of the development history of cation battery. In fact, cation battery appeared tens of years ago. The first cation system appeared in 1960s, and at that time, cation just used as additive as a primary thermal battery. Well, the first room temperature battery, cation battery was also studied by Dr. Auerbach in 1991, right? More than 20 years ago. At that time, he cycled the cation metal in different kinds of organic electrolyte, which have been developed in lithium-ion batteries. Unfortunately, it was reported that the cation metal was not reversible in these systems. So after that, you know, in 2000 or 90s, lithium-ion battery was successfully trapped in the market, right? So after that, the study of the cation battery just stopped. Well, the revive of the cation battery study comes back in 2015 when Professor Pellicin, which is a SPAN group, and Dr. P.G. Bruce in UK developed a new electrolyte system to realize the reversible stripping and plating of cation metal at the room temperature or high temperature. Okay, after that time, many researchers start to revisit the cation battery system. And following that, Professor Hui-Min Chen published a paper on dual-ion battery, used graphite as the cathode, but zinc as anode. And also Professor Linda and Dr. Zhao in Germany reported a new electrolyte system to enable the reversible stripping and the plating of the cation metal. So here is the brief historical development line of cation battery or cation metal battery. Okay, so you can see that from this this historical development, most work focused on the development of electrolyte or cation metal. Few work focus on the voltage, the anode or cathode materials. Well, if we want to develop or realize the commercialize of cation battery, we need to find a suitable anode and cathode materials, just like what happens to the lithium-ion battery. So that is what my group worked on. Well, for the anode material, our first choice is graphite. Why? Because graphite is the commercial anode material in lithium-ion battery. Even after 30 years development, graphite is still the standard anode for lithium-ion battery, right? And graphite has also been used for the other battery systems like a calcium-ion battery or aluminum-ion battery. So here is what I mentioned before that, the ionic liquid electrolyte to integrate aluminum within graphite layers. The sodium battery is also fine to use graphite as the anode. Here I want to spend 1 more minute to explain the history of the sodium battery development study for using the graphite anode. Well, at the beginning, it was believed that graphite is infeasible to store sodium because thermodynamic analysis shows that the intercalation of sodium ion into graphite is thermodynamically positive, right? So when we look at, when we recall our physical chemistry knowledge, we know that if the delta G is positive, it is infeasible to include the metal ion into the graphite. But later, in 2019, our group, my study demonstrated that we can use ether-based electrolyte to solvate the sodium ion to co-intercalate into graphite. So we call it the co-intercalation reaction. And so using this co-intercalation reaction, large amount of sodium ion can be intercalated into the graphite galleries and cycle over thousands of times with no obvious capacity degradation. So here we can say that it's very feasible to develop graphite as a universal anode for the battery systems. Well, it is not straightforward to intercalate calcium ion into graphite. And the first paper reported for the intercalation of calcium into graphite appeared in 2005 when they studied this calcium intercalated graphite using this method at high temperature to for the superconductivity study. But this compound need to be synthesized at a very high temperature and for a long time. And then later, a researcher tried to intercalate calcium by a solvent co-intercalation reaction and use En as a solvent and the calcium metal and store this compound for several days at 100 degrees C, and finally they got this intercalated compound. But no reversible intercalation of calcium in the graphite at room temperature have been reported. So how can we intercalate calcium ion into graphite reversibly at room temperature will be an important task. Well, by screening a lot of possible electrolytes, we found that for the first time that in DMAC electrolyte, which is this kind of solvent, use calcium BH4 as salt, we found that the calcium ion can be intercalated into the graphite galleries in the electrochemical system, which process is quite reversible. You can see that intercalation capacity is around 100 milliamp per gram, and which is very reversible. And when we cycle this cell, I found that it's quite stable for over 200 cycles, almost no capacity degradation. And when we increase the cyclic current density from 50 milliamp per gram to 2000 milliamp per gram by 40 times, the reversible capacity retention is very high, it's over 70%. So this electrochemical performance tells us two messages. Number one, the calcium intercalation into graphite is very stable using this electrolyte. Number two, this intercalation process is very fast with high kinetics, with high capacity retentions at high current densities, right? So now next we need to understand this system, why and how the calcium ion is intercalated into the graphite using this new electrolytes. First, we conduct the in situ XRD for the charge and discharge process. You can clearly a first view of this XRD image. You can see that this process is very reversible, right? So here is the graphite peak and expanded, and then during de-intercalation, it was come back. Right? It's very reversible. Using Braggs law, we can calculate the Miller index of each peaks. Okay, well, we can say that at the first several stages, with the intercalation of graphite, the intercalation of calcium ion, the peak shifted to lower angle, which means the expansion of the graphite galleries. When we go to here, there is no further change. It becomes, we call it a stage, right? Stage. So that means at this stage, there is no further expansion of the graphite galleries, but there is still continuous intercalation of the calcium ion. But later, that is shifted to another stage. We call it 003 by calculating the Miller index. And for the adjacent stage, you can say that the delta C, I mean the lattice change of the continuous stage, their difference is 3.4 angstrom. So 3.4 angstrom is exactly the single layer graphite distance, right? So that means it's a staging precise. Well, for the staging precise, we finally the final interlayer space between two graphite is 14.4. No, here is not angstrom, nanometer. Sorry, here should be angstrom. Okay, angstrom. So it's around 4 times of the single layer graphite. So that means the final intercalated graphite should be stage 4, stage 3, stage 1, or stage 2. Okay, and here I want to give you a very brief description of the staging precise. The staging precise, which is very familiar for the graphite, I mean the lithium-ion battery, where lithium-ion are integrated into the graphite. The staging process like this. Here is graphite. At the beginning, the lithium-ion or some metal ion integrated into the graphite. We call it dilute stage. And then stage 4. Stage 4 means every 4 layer of graphite are integrated with the metal ion. So here is the metal ion, and for this layer, we have metal ion. Then we go to stage 3. So every 3 layer of graphene are integrated with a metal ion. Finally, we go to stage 2. Okay, we just assume that the final stage, intercalation stage, is stage 2. And here we have a problem that, well, for the staging process, we have several models. Well, the 2 most representative one are Rudolph-Hoffmann model and the Dormans-Harold model. Well, for this one, I mean, Rudolph-Hoffmann model is direct intercalation of the metal ion, and but for this model, it's hard to explain the transformation from stage 3 to stage 2. So you can imagine when the stage 3 is formed. So how can you form a stage 2, right? You need to extract all the calcium ion into this layer and integrate with this layer, right? So, but anyway, for the fifth change of the stage change is a little complicated and still remain an open question. So here I will not expand. Well, when you remember that the fully integrated graphite, the interlayer space of 2 graphite layer, I mean the 2 integrated graphite layer is 14 angstrom, right? 14 angstrom. The volume expansion is over 300%. Well, if only the the bare calcium ion are integrated into the graphite gallery, the volume expansion should not be so large, right? So the volume expansion is so huge. We imagine that the soft molecule should be maybe co-integrated together with the calcium ion. To have evidence of this hypothesis, we conducted the NMR characterization. We characterized the DMAC solvent, DMAC electrolyte, and the calcium graphite. And the DMAC solvent have 4 carbon atoms, which refers to these 4 carbon atoms. And after it was mixed with the calcium salt, a clear negative, positive shift of carbon 2, 3, and 4 can be observed. Okay, so when you look at 2, 3, and 4 carbon, it shows that they are closely linked to the nitrogen and oxygen. That is because of the electronegative oxygen, electronegative nitrogen will form electrostatic force with a positive charged cation ion during the solvation process, right? And after co-intercalation, intercalation, you can clearly observe the peaks referring to the DMAC solvent. So it shows the DMAC solvent may co-intercalated with the cation ion together into the graphite galleries. Well, here is just the NMR evidence. We also conducted the FTIR or Raman spectra to show that DMAC are integrated together into the graphite. Now, we know that now we have demonstrated that the DMAC are integrated together with cation into the graphite. So how many DMAC molecule is coordinated with one cation ion into the graphite? So to demonstrate this number, we measured the charge or discharge of the graphite at different capacities or different charging discharging stages. And then we plot a theoretical value. For example, we assume that there are 4 DMAC is solved with cation ion in the graphite. Then we can know how this is the mass change of the graphite, right? Then we also assume some others, 2, 3, 4, 5. We found that the 4, we will assume 4, the experimental data match well with the theoretical value. So that means every cation ion are coupled with 4 DMAC solvent in the graphite galleries. Okay. Now, and next question is, what is the configuration of your co-intercalated graphite compound? We already know the capacity of the graphite, and we already know how much solvent cation ion, and we also know the final the lattice parameter of the intercalated compound, right? So by DFT calculations, we found that it shall be stage 2. If stage 1, the final IC, lattice parameter is only 9 angstrom. It's different, far different from the 14 angstrom. If it's stage 3 or stage 4, the capacity is wrong, right? So stage 2 is the IC is 15 angstrom, is close to the experimental value, and the theoretical XRD also match well with the experimental results. Okay, and we also study the kinetics and by the CV scan. So you can see that it's determined by both the diffusion and capacitive. And something interesting is that we disassembled the cell and observed them on the TM. We found that there is no SEA layer, no visible SEA layer on the surface of graphites after several cycles, which is different from that in the lithium-ion battery, use graphite as the anode. That may be because of the co-intercalation reaction, which the cutoff voltage is high, and there is no desolvation process in the co-intercalation. So there is the SEI-free phenomena will be beneficial to the fast kinetics at what we observed for the rate performance. Okay, so here is our work for the development of anode material for calcium-ion battery. We use a commercial graphite in lithium-ion batteries in the new calcium-ion batteries. Next, we turn our eyes to the cathode material. Well, cathode material for lithium calcium batteries suffer 2 main problems. Number 1 is a large energy barrier for the calcium ion diffusion, because the calcium ion is a divalent ion and it's very large, right? And so here you can see that most of the reported calcium cathode materials present very high migration energy barriers above 1 eV. Okay, it's very hard for calcium diffusion in the host. Number 2 is a large volume expansion, because calcium ion is large. So some cathode materials present very large volume expansion. You can see over 10%, we will induce the degradation or pulverization of the host structure. So can we find some host structure enable rapid and stable cation insertion and extraction? We turn our eyes to the commercial cathode for sodium-ion battery. Okay, sodium-ion battery, NVPF. So sodium vanadium fluorophosphate. I think Dr. Zhang just mentioned that before. And well, sodium NVPF have been commercialized in some companies like TMAT in France, Hainan China, and also a US company. And compared to the layered structure in the sodium-ion batteries, the NVPF, which is a polyanionic structure, hold the 3D framework, which is wall expansion insensitive when intercalate, when storing the large ions or cations. Okay, so we tried the NVPF structure, and fortunately we found that it's very stable and very promising. So here is the NVPF structure. We extract the cation sodium ion first to create vacancies in the sodium site, and compound them, pair it with the active carbon, the counter electrode, because of the troublesome cation metal and the lack of suitable electrolytes. Okay, so in this semi-half cell, we can say that its reversibility is very good. Okay, for the first 10 cycles, you cannot observe any capacity degradation, right? And the cation storage capacity is also very high. It's only 0.35 cation per unit. And for the rate capability, we can say that when we increase the current density from 10 to 500 by 50 times, the capacity retention is also acceptable, right? Acceptable. Well, what's impressive is the cyclic stability is very, very high, almost the best reported up to now for the cation-ion batteries. After 500 cycles, the capacity retention is over 90%, and the coulombic efficiency is also close to 100%. So that means this material is very, very promising for the new cation-ion battery system as a cathode material. Now, next we have some questions to answer. Number one, why it is so stable? You have mentioned that, I have mentioned before that most of the reported cathodes are very unstable. They can only cycle 100 or several tens cycles, while you can stable 500 cycles. So here we conducted the synchrotron in situ XRD for this system during cathode and discathode for 1 cycle. You can see that a first place shows that it's very reversible for this structure, right? And there are also some phase separation because of the relatively slow kinetics for the cation system. We can calculate the lattice parameters of the NVPF for A and C. C means the height of the layered structure. You can see, I may go to last slide. C means in this direction, C means in the Z direction, and AB means the panel direction. And you can see during the intercalation, the C decrease. That is because of the intercalation of the cation ion shared the oxygen layer, which induced the shared oxygen layer, so that the repulsion between shared the oxygen layer, that the repulsion of the adjacent layer will be reduced. So, and for A, because of the valence of vanishing change. So for the B, you can say for the B, it will increase. So the adverse change of A parameter A and C leads to a very low wall expansion, only 1.4%. Well, you may ask, your host material is from sodium battery. So what is the sodium? What about in sodium battery? In sodium battery, the NVPF structure, the wall expansion is 2.9%. But why your wall expansion is even lower than your host structure? That is because you remember cation is a divalent divalent ion. So we only need to occupy half of the space left by sodium. So that is why it's super stable, super small for the wall expansion. So here explain why the structure is very stable. Next, we go to the kinetics and we conduct the GITD analysis and calculate the cation ion diffusion coefficient, which is very fast. And from the DFT calculations, we found that the intro and interdiffusion energy barrier for the cation ion is very small. It's only 250 or 600 millieV, which is much, much lower than the 1 eV reported for most cathode materials for cation ion batteries. Okay, so next we need to explain where your cation ion are stored in the host. We conducted the powder X-ray characterization and plot the sodium ion host space. We have sodium 1 and sodium 2. You can see here, sodium have 2 spaces to store the sodium. After extraction of the sodium, most of the sodium 1 we extracted. So here we have the space, right? And during the cationation, the cation ion will occupy many sodium ion space, sodium 1 sites. And during decationation, most of the cation ion are extracted. So it's very reversible. And this reversibility also confirmed by the valence redox centers valence change. We measured the vanadium redox centers valence change using X-sense. You can see the reversible shift, negative and positive shift of the vanadium. And we also conducted the sodium NMR because we have a sodium 2, right? We have a sodium 2 left. We can measure the sodium 2's the local environment to explain the cation ion inside. So you can see that after sodium extraction, here in 2, most sodium 2, and after cation intercalation is negative shift because of the valence change of the vanadium. And also when we didn't decalciate, it returned to back. So that means this process is very reversible. And we can also use TIA to directly observe the cation. We can say that seeing is believing. So here you can say we have the cation signal using the Yale spectra. Okay, so as a summary, using the NVPF host, the story is like this. We extract the sodium ion in the sodium 1 space, and then during charge and discharge, sodium ion are just extracted and inserted at within the host structure without any without obvious volume change. Now, next we studied the voltage, because for cathode material, we want high voltage, right? And we found that if we change the fluoride content, for example, we change the fluoride content to y equal to 0 to y equal to 1, you can see that apparent upshifts of the potential can be observed. So you can see when we use y equal to 0, that means fluoride is 0.5. And for y equal to 1, that means all the oxygen occupied by fluoride. So there is apparent voltage increase. So well, it is related to the inductive effect between the fluoride, fluorine, and the PF4. So here I will not extend because the time is limited. And electrochemical measurements show that the high voltage cycle stability is very good. Also the capacitor retention. And well, even although we replace some of the oxygen with the electronegative oxygen, fluorine, we can say that the charge transfer kinetics was not affected too much. I mean, the diffusion kinetics also maintained below 1 eV. Okay, so that means this cathode can also be stably cycled. Now, we have a stable cathode and stable anode. You must the idea come to direct to our mind is that why to combine them together into a calcium ion full cell, right? So yes, we did that, but it was not straightforward and not so successful. If we combine graphite and MVPF cathode, we found that there is incompatibility of the electrolyte between two sides, because for graphite we need a special electrolyte for co-intercalation, but the electrolyte is not stable at high voltage. For cathode, we need a high voltage electrolyte for its high voltage, right? But for this cathode electrolyte is not infeasible for the graphite. Okay, so we prepare such a immiscible dual phase electrolyte. We call it thermodynamic immiscible dual phase electrolyte, and attempt to construct the graphite MVPF full cell. Although the cyclic stability and capacity is not good, but it's opened a new avenue and give us a promising signal for the future work. So, and we also secure a fund based on this, and I think I can report this in the future. And next, we also couple the calcium metal with MVPF cathode with the most updated electrolyte developed by Professor Zhao in Germany. And it was found that use this new electrolyte, we can successfully prepare a high voltage calcium metal full cell. Okay, you can see the voltage is very high, it's only 3.7 volts. Well, same, though you can say that stability is bad. Well, that is maybe because of the instability of the electrolyte, because you can say we use ether as a solvent. Ether is unstable at high voltage, right? And it may also relate to the instability of the calcium metal. But anyway, this is a successful try. So here I give a summary. And well, calcium ion battery study is relatively a new field with very few reported works, and our group mainly focus on the exploration of the electrode materials, including the anode material and cathode material. We found that the graphite, which is a commercial anode lithium-ion battery, is feasible to store calcium ion using the co-intercalation reaction. Well, polyanionic MVPF cathode, which is commercial in sodium-ion battery, is very promising to solve as cathode, the high voltage cathodes. But if we want to demonstrate the calcium ion battery with the rocking chair mechanism, it's be very hard. There is still a long way to go. Okay? And you are welcome to collaborate with us for this system. Okay. Finally, I would thank my team and some grants. Thank you. Thank you for your attention here. Yeah.